Hi, my name is Hamed Karimipur, and in this flash talk, I'll be briefly talking about 3 online studies that we have done on a new algorithm to specify the color of surfaces. The key problem that can arise when specifying object's color is that two patches might be seen as having the same color under one light source, as can be seen here on the left side, but different colors when seen under another light source, as shown here on the right side. Why does this problem happen? Because the reflected light towards our eyes combines the spectral information of the light source and also the surface of the object. Mathematically speaking, when specifying surface colors, we multiply surface reflectance spectrum, illuminant or the spectrum of the illumination, and the cone sensitivities. Surface reflectance spectrum shows the proportion of the light that gets reflected off the object's surface at each wavelength after hitting it. This proportion is shown for a given object surface on the y-axis, and the x-axis shows the range of the wavelength. Illuminants show the amount of the light energy at each wavelength for the light source. Here we can see that this kind of color specification is not independent of the illuminant, which might cause some irreversible damages to human valuable heritage. For instance, as you see in the painting from Picasso taken from Roy Byrne's book, there are some purple stains. When this painting was being restored under one illumination, the purple stains didn't show up. However, when the painting was shown under another illumination, it turned out that the pigment used while restoring didn't match the pigments in the other part. But the importance of the color specification is not restricted to only painting, but it is also central to industry wherever pigments and dyes are used, like car industries. One solution to avoid these damages is using only the spectral information of the object that is independent of the light. On the left side, you see the spectrum, and on the table, you can see the measurement for each 10 nanometer intervals. Now, because this is characteristic to the object surface, it can be used to precisely specify its surface color independent of the light. However, just imagine how practically inconvenient it could be if we use the amount of the reflected light at each wavelength, because we end up using many numbers to specify a single color. More importantly, these numbers don't provide us with any perceptual information. To characterize surface colors independent of the light by many fewer numbers rather than the full spectrum, previous studies proposed a simple linear transformation. Having fewer numbers, this transformation is practically more convenient to communicate than the full spectrum. Mathematically, matrix A in the center here converts illumination color signal to the reflected light color signal. Can we use this model to specify surface colors? Considering the sensitivity of human color perception, it is yet not clear how well and precisely this simple linear transformation works. For this, we tested under what kind of illumination people can see the difference between color approximated based on the transformation and the color produced by the spectral information, and we used hyperspectral images of naturalistic scenes as stimuli. Hyperspectral images are the images where the spectral information is available for each single pixel. As a result, they are very large files. Here you can see the variety of hyperspectral images we use in our studies. The colors in these images cover a large part of the perceptual color space so that we can make sure that the results don't depend on the color. Then we rendered each scene under two types of illuminants, narrowband and broadband, because bandwidth has a major effect on the rendering of surface colors. Natural lights have rather broadband spectra, while artificial lights like LED have narrowband spectrum. For both narrowband and broadband, we sampled 8 illuminants so that we can cover 8 color directions, as can be seen in the lower image. As I mentioned earlier, we aimed at testing whether people can see the differences between the approximated rendering based on the transformation and the original spectral rendering. For this, in each trial, 4 images were shown. 3 of them were exactly the same, and they were spectrally rendered images. The other one was rendered based on our approximation. Then observers were asked to spot a different image, which here is the top right. This one is obviously different because as we can see later from the results, the differences between approximated rendering and spectral rendering for narrowband illuminance are visible to our eyes. We conducted 3 studies with many participants, and in each study we had 8 illuminants and 4 scenes, which resulted in 32 trials. Here we can see the results for the scene shown above on the narrowband illuminance. The 4 bars correspond to 4 illumination colors in our studies, and the error bar shows 95% confidence interval. Statistically speaking, each image here has 25% chance of being randomly selected, so where our algorithm didn't work, participants managed to spot a different one. As a result, the proportion of correct responses, or as we named it on the y-axis, accuracy, should be significantly higher from the chance level, which is shown here by the dashed line. As you can see from the bar chart, the participants responded above chance level for this scene on the red, yellow, and blue narrowband illuminance color. We got almost the same result for other scenes on the narrowband illuminance, which shows that our algorithm didn't work for narrowband ones. However, those narrowband illuminants are rare in the natural environment. Here are the results for broadband illuminants, which are much closer to the effect of natural light. These results show a relative success compared to the narrowband ones, and they hold for the images across the 3 studies, although there are a few exceptions where participants were slightly but significantly over the chance level with the broadband illuminants. To conclude, the approximated rendering under most cases of broadband illuminance is indistinguishable from a spectral rendering. Remember that broadband illuminants are similar to the illuminants in the natural environment. As a result, we can say that the approximated rendering can be used to precisely and reliably specify colors of object surfaces in the natural environment, but we still can't use it on the artificial illuminants. However, we need also to do the experiment in a lab setting under controlled condition to see if we get the same results. And also, our approximation compresses large hyperspectral images without losing visually noticeable color information. And finally, it speeds up surface color computation. Thank you for taking time, and I'll be happy to answer your questions regarding this topic in the corresponding